5 equations that made history. 1. E equals mc squared. This equation was formulated by Albert Einstein in 1905. It describes mass-energy equivalence. Energy is equal to mass times the speed of light squared. This means that changes in mass will result in changes in energy. Any object contains potential energy, even if it's not moving. Under the right conditions, energy can become mass, and vice versa. Pure energy is electromagnetic radiation traveling at the speed of light. Einstein's equation is what enabled us to obtain nuclear energy. 2. Maxwell's equations. James Clerk Maxwell studied electricity and magnetism. These forces were poorly understood in the 1800s. In 1864, Maxwell published a list of 20 equations. They described how electricity and magnetism worked. The formulas also showed their interrelation. Maxwell's 4 most important equations are still taught in college. They provide a basis for every piece of electronics in our world. 3. Calculus. Calculus is a mathematical study of continuous change. It was developed independently by Newton and Leibniz in the 17th century. Initially, it was called the calculus of infinitesimals. It dealt with the convergence of infinite series as they approach a defined limit. From this originated differential calculus and integral calculus. Differential calculus studies derivatives of a function. Integrals describe the area underneath a curve on a graph. Calculus is what underlies all modern physics, economics, and engineering. 4. A squared plus b squared equals c squared. This equation was formulated by Pythagoras. It underlies the Pythagorean theorem. It describes the relationship between the 2 legs of a right triangle and its hypotenuse. The hypotenuse is the side opposite the right angle. It makes up one side of a square. The area of that square equals the combined areas of the squares on the other 2 sides. The theorem is the basis of geometry and algebra. 5. Law of universal gravitation. This law was formulated by Isaac Newton in 1686. The law states that every particle attracts every other particle in the universe. The force of that attraction is directly proportional to the product of their masses. It is inversely proportional to the square of the distance between their centers. The equation describes all motion in the universe. It has since been superseded by Einstein's theory of general relativity. But relativity is generally only used when extreme accuracy is required. Newton's law perfectly describes most interactions we see around us. It's part of classical mechanics and has been used in engineering for centuries.